So with our app complete in terms of its user functionality, it's time to focus our attention on deployment and issues such as scaling. Now our app categorically looks like this. We've got Express, below which we've got SocketIO, and in this case, we have a single instance of this app running on a single machine or a single server. As long as that holds true, SocketIO will work fine in general. But what you should know is that SocketIO uses an internal buffer for holding and transporting messages across two rooms and users. By default, it uses the server's memory for this purpose. Memory, as you can well imagine, is not designed for scalability. But let us assume for now that we are running this on a low traffic single server instance on the cloud and everything works well. This, however, will not fare well if the traffic spikes up massively. In that situation, you would need a setup like this. Node.js apps can be made to run across multiple server instances, and that is a subject which I'll talk more about in a later section. We will not be scaling our app beyond one processor instance for this example, but it's suffice to say that on cloud providers such as Heroku, you can easily scale your app to run across multiple processor and server instances. This is at the core of scalability on the cloud. When your traffic spikes up, you spin up more server instances and you can dynamically spin them down when not needed. In such a case, a load balancer sits between the client and the app servers, and it does the job of seamlessly routing traffic to app instances where the load is manageable. So a user who was served by server 1 first might not be served by server 1 again if the load balancer decides to route traffic to another server in the cluster. This presents us with a few challenges. If you're not using a session store like MongoDB, for instance, then session data that exists on server 1 may not be available when the request next reaches server 2, for instance. That is why we repurposed our MongoDB connection through Mongoose to work with the Express session middleware so that such a problem doesn't occur and we've got our data stored in one unified data store. This problem affects two other areas in our app. I'll solve one while the other will be discussed in the last screencast for this particular section. What we'll discuss here is the way SocketIO works with regards to scalability. You can easily run SocketIO in a clustered environment, though we'll not go into that for now. By default, SocketIO uses the server's memory for the purposes of the buffer and transport. And when the app is running across multiple servers, it becomes a roadblock for us because messages originating from one process or server and destined for a room will not reach across servers and nodes because rooms and namespaces exist in the server's own memory and may not be present on other servers in the cluster. This routing of messages across rooms is handled internally by SocketIO's adapter module. By default, this adapter uses the server's memory, but it can be adapted to work with a fast data store or a database where everything is universally stored. This is where Redis comes into the picture. Note that for actually setting up and scaling, you require setting up a load balancer and a reverse proxy server like Nginx, which is also demonstrated later in this course. And this process works as long as you are on WebSockets. For backward compatibility with long polling, however, a few additional steps are needed, which you can read about in the SocketIO docs on SocketIO's website. Another critical issue is session affinity. In simple words, a WebSockets session request originating from SocketIO running in one process or a server should be routed back to the same process, or else a socket connection will not persist. This is also known as a sticky session. Though there are various modules available for implementing sticky session ability in our app's server core, on Heroku, this is a feature that we can simply enable with a single command. Implementations of a sticky session or session affinity involves identifying a server instance using its IP or even a browser cookie. With SocketIO, the problem is that session affinity is only supported as long as your transport is over WebSockets and not on long polling. Fortunately, we can force SocketIO to only use WebSocket as its transport. Do note here that though we are implementing Redis, there are other steps that are also needed to realize the full benefits of using a Redis-based adapter, and those have been briefly discussed in the last screencast in this series, though we will not be implementing them for this example. Alright, now in the simplest of words, Redis is a database server. However, unlike databases like MongoDB, it isn't disk-based at its core. Rather, it stores everything in memory and uses the disk for persistence and to ensure that it doesn't run out of space, unlike how memory works. Since it offers the best of disk with the speed of in-memory transactions, it is most suited as a cache and for storing sessions and to use with SocketIO as an adapter interface. Unlike RAM, you don't run out of storage and you don't lose data if the server restarts because Redis takes snapshots of data that it holds in memory on disk, thereby ensuring persistence. You can easily replace MongoDB in our app with Redis for using with the Express Session middleware. However, we'll leave that for now. What we'll use Redis for instead is as an adapter for SocketIO. Redis is typically available for Linux, but there are ports for Windows as well. Since I'm using a Mac as my main development machine for this project, I'll take a slight detour and will demonstrate how Redis can be installed on a Windows 10 machine. We'll then get back to installation and the rest of the code on the Mac. Alright, one way to install Redis on Windows is to download the source code from the Redis website and then use Visual Studio to compile two binaries for the flavor of Windows that you're using. This seems like a rather painful way, so let me show you an easier way out. For this purpose, we'll use a package manager for Windows called SocketIO. Think of it as apt-get or npm but for Windows-based packages. To install SocketIO first, go to socketio.org, scroll down and copy this bit of command prompt code from here. Then open a command prompt in administrator mode. On Windows 10, this can be done by right-clicking on the Windows button. Make sure you open the command prompt in admin mode or else the installation won't work. Once open, paste the text you copied earlier and press enter. This would start installing SocketIO and it takes a while. I'm going to speed up the recording to skip over this part. Once you reach back the prompt, exit and reopen the command prompt in admin mode. If you now type commands like choco list ~local -only and press enter, you can see the SocketIO installer in action as it shows you a list of packages that it has installed locally on your machine. If you type choco search Redis, then you will see a number of entries from SocketIO's online registry which contain the words REDIS. Now for the main part, for installing the 64-bit edition of Redis, I'll type choco install redis-64 and press enter. This will download and compile Redis for your machine. This in fact configures everything for you. So if you type redis-server and press enter, you can see the Redis server fires up on port 6379. Now let's continue with installing Redis on our Mac and writing the rest of our code. So head over to redis.io, the official site for Redis, and click on the latest stable version as listed on this site. At the time of this recording, I can see version 3.0.7 listed here. Once you have the gzip file on disk, open a new terminal window and type tar xzf followed by the name and path to the gzip file, like so, to extract it to a folder. Now browse into the newly created folder, which is Redis 3.0.7 in my case, and let's examine the contents. The first thing you need to do when you download Redis is to build a binary executable as per your flavor of Linux. This is made possible by the make command, which internally uses the cc or gcc compiler to link and compile down C or C++ files. So to get started with this process, type make inside the Redis folder and press enter. This will take a while and will compile and build Redis for use. Once done, your compiled binaries reside in a folder called src inside the Redis folder. So to get the Redis server up and running, type /src/redis-server and press enter. You'll notice that Redis instantly fires up and is ready to accept connections on port 6379. Now make sure you don't close this terminal window where Redis is running, and you'll need to do this every time you want to run your app once we have done the integration in this screencast. Back to our ChatCat terminal, we'll first download two modules that will let us integrate Redis with SocketIO. The first is a Redis driver module for Node.js. This will help us connect to Redis. So using npm, install the Redis module, and I'm using version 2.4.2 for this example. Once this is down, then we'll download socket.io-redis. This is the adapter module for socket.io that will let us switch out the memory-based store for Redis. Next, go in your development.json and we'll create a new configuration block called Redis, where we'll put three keys. A host, which in this case of a local server will be 127.0.0.1 or localhost. The port, which we know is 6379. And the password field, which we'll set to blank because no password has been set by default, and we'll keep it this way. However, things are a bit different when we come to the production environment. When you deploy your app on Heroku and provision a Redis store, you will not be given the hostname, password, and port keys separately. They will instead be made available through an environment variable called Redis_URL. And it will resolve to a Redis URL, which will look like this. The part before the @ and after the colon denotes the password, while the portion immediately after the @ is the host followed by the port number. So what we'll do is parse this URL to extract these three keys dynamically. I'll thus create a variable called Redis URI, where I'll bring in the URL module that you've seen in the fundamentals section, and we'll use its parse method to directly parse the contents of the Redis_URL environment variable. Note that I'm doing all of this in the block that will execute when our app runs in production mode. By using the URL.parse method, we'll be able to directly extract the hostname and port number like so. This can be used directly as is. For the password, however, we'll access this entire component of the URL and we'll extract the second part of this string, which is where the password is. The first part before the colon is irrelevant. Now URL.parse will provide us with this entire string when we access the auth key. So in a new variable called Redis password, access Redis URI.auth and then use the split method to break apart this string where the separator is a colon. This will break this string into two elements and will return an array. We can then directly access the second element with the index number 1 to get the password. The first element, that is the part before the colon, will be accessible by index number 0, but we don't need that part anyway. So this is how we load in access credentials for Redis, be it our local installation or on Heroku. Now let's go into our app's core index file, where we had instantiated the server with SocketIO integrated in. Let's bring in the Redis module first by using the require statement, and specifically we want to bring in the create client method like so. This method will let us create an instance of a client interface that can be used for interacting with Redis. Also get the socket.io-redis adapter module as well. Now, one thing you'll need to understand here is that we want our socket.io to send and receive its buffer from Redis. For sending or publishing first, let's instantiate a client interface. We'll call it pub_client. This can be done by invoking the create client method using the Redis keyword and first passing in the port number, followed by host, and then in an object, create a key called auth_pass and set it to the password. You can see that we can conveniently access the Redis configuration using the config module. While this interface will be used for strictly sending or publishing data buffers, we will create another instance called subclient, which will be used to subscribe or get data back from Redis. So invoke Redis as before. Only this time we'll add another property called return_buffers and we'll set it to true. Okay, why did we use two separate interfaces? Well, the Redis driver that we are using doesn't accept a password by default. So if you're going to use authentication using password as it will happen in production, the only way is to create two separate interfaces where the create client method provides us with a way to use a password using the auth_pass property. The return_buffers property is absolutely needed here, because if you don't use it, then Redis will return data as a string, whereas we want the data in its original buffer state. By setting return buffers to true, the Redis client will return data in its original state without unnecessarily stringifying it first. Now, for interfacing Redis with socket.io, use the io.adapter method, which will allow us to specify a custom socket.io adapter. In this case, we'll use the adapter keyword, which refers to the socket.io-redis module, and for its options, we'll pass in an object containing two key value pairs as pub_client and subclient. I'm using the shorthand notations because both these properties are spelt exactly how we have created our variables. Now remember, I had mentioned a few minutes ago that we also require session affinity support on our server. This also means that we'll have to force socket.io to only use WebSockets as its transport medium. So let's force socket.io to only use WebSockets. This will be a twofold process. First, here in this file, we'll type io.set, and in the brackets, I'll first type transports in single quotes as the configuration key to set, and then as the second argument or as the value, I'll pass in an array containing a single value called WebSocket. Since you can enable multiple transports, we are using an array but with a single value as our setting. The second part of this process involves adjusting our client-side code to only use WebSockets as the transport. So first, I'll head into the rooms.ejs file and I'll add an object to the IO method where I'll set transports to an array with the WebSocket option. We'll repeat the same thing for the chatroom.ejs file as well. And that's it. Let's see if this works. And it does. Be advised that you may opt out of using Redis while you're building this app, but I feel it's a worthwhile learning exercise.